So we already, heard about the line of work on polynomial-based code, and there have also been some breakthroughs on list decoding expander-based code. I think Shashank was responsible for both line of work. But today we'll give us a survey talk on recent progress on list decoding of graph-based codes. Thank you.
Thanks. Okay, so let's start talking about these graph-based codes.
Where's our IT guy?
Start with the basic definitions of a code just to set some common notation. We'll deal with codes that are subsets of sigma to the n. Sigma would be the alphabet and n is a block length. We think of codes as encoding some k-length messages, which are k-length strings over the alphabet sigma. You encode them into objects inside this set C. So these in particular are n-length strings over sigma. And hopefully the code is designed in a way when this code word is passed through noisy channel. We get a noisy copy of this code word, and the code is designed in a way that facilitates recovery of byte just looking at byte. Okay. We say this code C is linear if it is not just a subset, if it's a subspace of sigma to the n. For that, we would want the sigma to be identified with some finite p. And we all know, I think, the definitions of rate and distance. It's just that I want to stress that in this talk, we'll always be thinking of it as fractions. So fractions between 0 to 1. Okay. So typically a code might look like this. You have a lot of code words. Y tilde would be a corruption of y, which if it is not too far, you can map it back, at least theoretically. We have the singleton bound, which says that there is some tension between rate and distance, which is to say the rate measures how many code words we have, distance is how sparse this is. Singleton bound says the sum of these two parameters cannot be more than 1. So in particular, for a rate R code, the best distance we can get is 1 minus R. And this implies that the unique decoding radius, which would be half of the distance if we want these balls to be disjoint, is at most 1 minus R. So even if we took the rate to be very small, the best unique decoding radius we can hope for is half. And these sort of parameters are achieved by Reed-Solomon codes. Singleton bound itself is an impossibility result. We saw Reed-Solomon codes in the last two talks, polynomial-based codes. But what we are interested in is less decoding when the fraction of error really goes beyond 50%. And the hope is that the number of code words is polynomial, if not 1. If there are too many code words, then it's probably hopeless to do any sort of error correction. And in some sense, this hope always comes true in the sense that there is always a threshold, which is between half the distance and the distance, up to which the list size is bounded. And when we are looking at distance that take the form 1 minus R, this threshold looks like 1 minus square root R. This is the Johnson bound. And there is so the Johnson bound says that the list is bounded up to 1 minus square root R. It does not say that there is an algorithm to find this list. That's the algorithmic task. So if we have this f tilde as the corrupted code word, then up to delta over 2, we know that there is only one code word, but up to j of delta also, we will have not too many code words. So the last two talks, we saw a lot of work on list decoding for algebraic codes. So very quick hand-marked results maybe. A lot of this line of work on list decoding algebraic codes started from works of Guruswamy and Sudan in late 90s, where we got results that said we can efficiently list decode up to the Johnson radius for any Reed-Solomon code. And then Guruswamy and Rudra, building on works of Parvaresh Vadi, showed that folded Reed-Solomon codes can achieve the optimal threshold that we can hope for, which is 1 minus R. And recently, we had the result by Chen and Zhang that showed that this list size can be made order 1 over epsilon, which is close to the optimal. So this is a fairly well-studied landscape. We have optimal radius, optimal list size, near linear time algorithms. We saw a glimpse into all of this last 2 talks. What I'm interested in is things beyond algebraic codes in this talk. And techniques for a lot of this list decoding in general tend to be very algebraic. A lot of the algorithms follow the outline coming from old work of Sudan that says that you use the corrupted code word to learn some multivariate polynomial, and then the list code words should pop out as the roots of this polynomial. Now, if the code does not have this sort of algebraic structure, it's not clear what to do interpolation with, what polynomial it would be roots of. There are these alternative code constructions based on sparse expander graphs. Includes in particular the works of Sept, Spielman, and then used in many other ways to design linear time codes. So linear time encodable, linear time decodable codes, unique decoders. These tend to be very flexible constructions, so they inherit a lot of local properties of codes, such as LDPCness, but even local correctability, etc. And these expander-based constructions tend to be friendlier to smaller alphabet. For polynomial-based constructions, for Reed-Solomon, for example, the alphabet size has to be at least the block length. Okay. But we know very little when it comes to list decoding for these sparse expander-based codes. In this talk, we'll talk some of the recent progress that has happened in this area. So how to design these list decoding algorithms for these graph-based codes. And we'll mostly deal with 3 examples, which are Tanner codes that are based on spectral expanders. So Tanner codes are codes that are defined on edges of a graph such that each vertex enforces a local code constraint on the neighborhood of edges. Then we have the Allen-Edmonds-Luby distance amplification scheme, which again uses expanders, and Tashma's explicit binary code near the GB bound. The idea is that in all of these cases, expansion not only benefits code design, but also the associated algorithm design. And these two are sort of go hand in hand. The same thing that allows you to argue about distance, etc., also allows you to talk about algorithms. And most of our techniques will come from a rich body of literature on solving constraint satisfaction problems on expanding instances. So constraint satisfaction problems like KXOR, or max correct, or unique games, people have studied instances that are expanding there. And there are broadly 2 types of techniques that work there. One is based on the sum of squares optimization hierarchy. The other one is based on algorithmic regularity lemmas. And both of these will have analogs in the decoding world as well. Most of what I described until now is about the algorithmic aspects of it. There's also the combinatorial question itself. And you'll see more about that in the next talk by Madhu. So in this talk, as a running example, I'll focus mostly on the AEL amplification scheme, and in terms of techniques, the regularity lemma part of it. Okay. So let's see what this AEL construction is. It allows us to construct codes that have rate r and distance 1 minus r minus epsilon, so near MDS. In fact, it does so by starting from any high rate base code. It is an amplification scheme. If it's high rate, it must have had low distance. We can increase its distance to whatever we desire, and rate falls near optimally according to that. So originally, these codes were introduced to correct optimal amount of erasures in linear time. And then later, Guruswamy and Indic also used them to show design optimal unique decodable codes. The optimal unique decoding radius would be 1 minus r over 2. We can get arbitrarily close to that. the cost for this gap to optimal radius just gets passed to the alphabet size. And it's nice because alphabet size depends on epsilon, but not on the block length n. Another set of codes that have this feature are the AG codes, but then they tend to be far more complicated. These are much simpler. And like I mentioned before, this is a flexible construction. It inherits a lot of local properties from the base code that we started with. It uses, crucially, these bipartite spectral expanders. Let's only worry about balanced bipartite spectral expanders with degrees being d on both sides and n vertices on both sides. And we say it's a lambda expander. If we look at this L by R adjacency matrix, its largest singular value should be bounded by lambda times d. So d is just a normalization factor. Lambda will be between 0 and 1. And we want lambda to be as small as possible. So if you just take the complete bipartite graph, it will turn out to be 0 expander. But most applications would require us to take sparser graphs. And if we just take the double cover of Ramanujan graphs, for which we do know of explicit constructions, then lambda can be taken to be less than equal to 2 over square root d. By making d larger, you can choose lambda to be as small as possible. And the key property from these graphs that we will want is the expander mixing lemma, which says that if the degree is d over n is roughly the global density of edges. And between any two sets S and T, so S is a subset of L, T is a subset of R, the number of edges is roughly global density times the number of slots between them. The number of slots is S times T. D over N is the global density. You roughly expect the number of edges to concentrate around that. And this, the lambda times n term should be seen as, sorry, it should be lambda d times n. That should just be seen as an error term. What does this amplification scheme looks like? Let's quickly recap what concatenated code constructions look like. Let's say we have an outer code. The concatenated construction just looks at each coordinate of an outer code and further encodes it using an inner code. And for concatenated code, we know that the final rate and distance are both just the product of corresponding rates and distances. AEL construction is a twist on top of this, where we first do the concatenation until we get something as a concatenated code. But then we assume that this was happening on a bipartite graph, so that the concatenated code lives on the edges. But then there is this right vertex structure that we have not used at all. So you use this right vertex structure to fold all of these edges into D at a time into new alphabet symbols. So it's really just a folded concatenated construction, where the folding is done via this expander graph based structure. Because expander graphs are supposed to be pseudo-random, you expect this folding to be done roughly pseudo-randomly. The nice thing is that when we do this folding, the rate remains unchanged, but the distance really improves. So previously, the distance was delta out times delta in. Now the distance, there is a decoupling between delta in and delta out. And you can make the distance as close to delta in as you want by choosing lambda to be even smaller. Whatever delta out is, we'll choose lambda to be even smaller and then get as close to delta in as well. There's folding going on here. And roughly the idea is that even if two strings were to differ in very few positions on the left, the pseudo-random structure ensures that they differ in a lot of positions on the right. So very few differences on the left is sufficient to ensure a lot of differences on the right. So this is our main result. It's to list decode these AEL codes in near linear time. So recall that the AEL amplification looked like this. We started from a base code. We got rate R, distance 1 minus R minus epsilon, and the alphabet was some constant depending only on epsilon. What our result says is that these are also less decodable up to 1 minus r minus epsilon radius in near linear time. This is under some appropriate initialization. So we need to choose the inner codes appropriately. Really what our algorithm is a reduction from decoding these 1 minus r minus epsilon errors to decoding an arbitrarily small constant fraction of errors for the starting code. So you can initialize with any base code that is decodable up to some constant fraction, and then this reduction will work. As written, this is randomized. It can be made deterministic, but then this will no longer be near linear time. It will be some fixed polynomial. And as I mentioned before, unique decoding for these codes is just linear time. All of that still holds. This is just additional features on top.
So just to clarify, so since you do this reduction, are you just kind of assuming that C base is like constant size and then you just do kind of a brute force list?
No, C base is not constant size. C base is a global code. You do want it to be efficiently decodable. There is the inner code.
Yeah.
That is constant size. But I'm hiding that here.
So you'll be using a decoding algorithm for C base as a black box?
Yes.
Yes. So all you need is some basic amount of unique decoding.
Sorry, I forgot your name. So CAL is the whole thing and C base is like the outer code.
Yes.
Yeah,
yes.
okay, now I okay.
So Shashank, what's going to go on here is like you're doing some like decoding to get something that's like close to a code word in C base.
Yes. And then only this final amount of unique decoding will be done by the base code because you're already very close to the true code word. And this was like recently there was a paper on archive. This was concurrently and independently also discovered by Fernando Singh. So let's see what the unique decoding algorithm looks like. This was supposed to be a linear time algorithm.
Can I just ask our question? So your result both gives a combinatorial result and an algorithmic result together? Like both were unknown before?
Yes, that's right.
And like and the combinatorial result just comes from the algorithmic result. There's no middle step. Okay.
Yeah. I'll come to that a bit more.
And you also need to choose the inner code in some way.
Yes. So we do need the inner code. I mean, it's sort of a local to global property transfer. So you want the local code to be really good with these properties.
At least decodable.
List decodable up to capacity with constant list sizes.
It doesn't give the optimal combinatorial result. It gives some combinatorial result.
It gives some combinatorial. In terms of radius, it is optimal, not in terms of lists.
Have you done unique decoding to half the minimum distance at this stage?
Yes. Yeah, so let's see the unique decoding algorithm and we'll see what breaks down when trying to do list decoding. Okay. So let me use the standard that G is going to be the receive word and H is going to be the true code word that we are looking for. And delta R just means that I'm looking at distance on the right hand side. So delta R G comma H is less than 1 minus R over 2. 1 minus R is the distance. We are under half of that. So how does the unique decoding algorithm work? Well, based on the G here, we can induce a bunch of local views for the same G. Because G, even though it was seen as a symbol in sigma into the D for each right vertex, it's really a labeling on the edges. Once you have labeling on the edges, you can look at the corresponding labelings on the left vertices. The unique decoder simply decodes each of these GIs that it sees on the left side. And we'll get some different H1 tilde, H2 tilde up to H7 in this case. And then it applies the base code, or what I was calling base code before, and outer code here. It applies the unique decoder of the outer code. Why does this work? The key claim is that because on the right we had G and H being closer than delta over 2, on the left for most vertices, we should have the local views also closer than delta over 2. This is sort of sampling property, and expanders excel as samplers. So each vertex here is sampling the global assignments G and H on the right. They have certain distance on the right. Each vertex here does a good job of witnessing that distance. And this concentration is super strong. So you can say that delta GL and HL is less than delta over 2 for all but a fraction of vertices that only depends on lambda. And by decreasing lambda, I can make it as small as I want.
But don't you have something, the delta over 2?
Yeah, so there is a bit of fudging. If one was minus epsilon, the other can be made minus 2 epsilon. But the point is that the number of left vertices for which this does not happen is so small that I can deal with any unique decoding radius for the base. Okay, so this is pretty much the best unique decoding radius we could hope for. It's parallel and everything. Every node makes its own decision. And then we rely on the base codes decoding. So let's try to generalize this to list decoding. This, as I said, was the sampler property. Now, again, we have this G, which looks like sigma into the D to the R, and now we'll have a bunch of GIs. Now, when we go to decode, let's say we are decoding up to 2 delta over 3, beyond delta over 2, then we need not have a unique code word. We will have to deal with more than one code words. And we'll get, let's say for simplicity, we have only lists of size 1 or 2. As we saw in previous talks, there's the higher order MDS code, which can be used to give this sort of inner code. But let's not worry about that too much. Let's say the lists are always of size 1 or 2. Now, we get these local lists at each left vertex. Any true code word, so similar sampler property can be used to say that for the true code word, it is always going to be represented in these lists. Whatever the local assignment corresponding to the true code word was. The only issue is we don't know which one. So for every left vertex, we have 2 choices. We don't know which of the 2 corresponds to the local code word. We know that it is present somewhere. This by itself can still be pretty expensive because for each of these n coordinates, in the worst case, I might have 2 choices. And we need to do something better than just doing a brute force search, which would be exponential time. Okay, so the main insight is that regularity lemmas can help us do this stitching of these assignments consistently. So we want to build a consistent assignment across all of these left nodes. And we are going to see that regularity lemmas are a useful tool for doing this. So what are these regularity lemmas? Let's take a more functional view of this. Let's forget about codes for some time. Let's say we have a complete bipartite graph, just k n comma n. And we fix any set B on the right. Then it's true that if I take any set A on the left, the number of edges between A and B only depend on the size of it. Because between any 2 sets A and B, the number of edges is just A times B, the sizes of the corresponding sets. This need not be true when we don't have a complete bipartite graph, of course, because the graph will have more structure. It's almost true in the sense that we have this regularity lemma for dense graphs that says that, okay, sure, maybe the edge count does not only depend on the size of A, but there is a partition of L into constantly many parts, such that this edge count between A and B only depends on the density of A under this partition B. So let's say there is a partition into 100 parts. What this says is that I don't really need to know what A exactly is, which would require me to know exactly what A is as a subset. I only need to know what is the intersection of A with the first part, with the second part, up to the 100th part, which is much lesser information than knowing the exact set A. Okay. All of this is up to some eta n square error. Eta is an arbitrarily small fraction, and the number of parts that we get depends on this eta. So the trivial thing would be taking eta to be 0, where you can exactly figure out what the number of edges is, but then the partition will have pretty much n parts. We want to use this when eta is a small but constant number.
And you can deal with, I mean, sometimes these regularity lemmas come with towers of.
Yeah, so we are only dealing with weak regularity lemmas where it's much more mild.
Okay.
It's like only exponential in 1/8.
Does it matter to your algorithm?
It doesn't matter, you'll have the corresponding dependence.
Also, you don't have a dense graph, right? So you'll use.
Yeah, so I'll come to the sparse graph analog.
The partition P has to depend on B, right?
No, so you can analogously also have a partition on the right. So really the statement is that there's a partition on the left, partition on the right, such that for any A and B, it only depends on the densities of A under that partition, densities of B under that partition. I don't care too much about the right side, so I'll just fix a set. Yeah, so Venkat said there is no, we are mostly dealing with the sparse graph setting. But thankfully, there's an analogous regularity lemma for the sparse graph setting also. First of all, what is the analog of complete graph for sparse graphs? It's just the expander. And there again, we have that for any set B, the edge count between A and B only depends on the size of A. And this is essentially the expander mixing lemma. Expander mixing lemma says that for any two sets A and B, the edge count only depends on the size of A, the size of B. It doesn't matter what those sets exactly are. And analogously, we have this sparse graph regularity lemma, which says that there is a partition P of L. Now the error is eta times ND, so it's normalized correctly. Previously, the error was eta times n square, such that this edge count only depends on the densities of A under this P.
So this regularity lemma is for general graphs, because you said for expanders it's already known. I mean, it's true for expanders.
It's true for subgraphs of expanders. So just like any dense graph is a subgraph of the complete graph, we look at any dense subgraph of an expander.
So it's true for expanders, and this lemma says that you can have a partition.
Yes.
And this actually relies on the fact that it's a spectral expander and not just on the expander mixing lemma.
I mean, the only part from the spectral expander that we use is the expander mixing lemma.
Okay, so it's not algebraic, it's combinatorial.
Like expander mixing lemma also implies spectral.
Right.
No, but the way that you stated the expander mixing lemma was not in its strongest form,
okay.
right?
Yeah, I think the weak version suffices.
Which means that it's a combinatoric state.
Yes. We don't need the stronger version. Okay, maybe that's not. I'll definitely need both sides of the expander mixing lemma, but I don't know about the error term if that's what you're talking about. So we have the regularity lemma for sparse graphs.
And so is this a lambda dependence here?
Yeah, so lambda will have to be small enough for all of this to happen. Thankfully, the lambda dependence does not really change our code's parameters, so we can take it to be as small as we want. It only goes into the alphabet size.
Okay.
And that helps our case.
Does it say that this O sub eta of 1 parts is like O sub eta lambda of 1?
Yes, not just that. Like lambda will have to be small enough with respect to this eta.
I see.
Only then this will be even true.
Okay.
And this statement, the regularity lemma for sparse graphs, this is well known or should be well known?
Should be.
I don't know what should be well known, but I think it's implicit in some old works from even 2008 etc. Maybe even a mix.
Do we detect level improved in a similar way, kind of with like a density increment?
Yes.
Yeah, so it's just if you follow that proof and like,
Yes.
yeah.
Yes.
It just use that.
Exactly. Yeah, you combine that density increment kind of argument with expander mixing lemma essentially.
And it's actually sort of, if you don't care about weak versus strong regularity, for strong regularity, there are much older statements of Kohayakawa and Rodel, which also prove regularity lemma for sparse graphs or subgraphs of expanders. For weak regularity, it was kind of implicit, and then various notions of implicit later.
And what is the constant for weak regularity? This order eta?
It's simply exponential in 1 over eta. Polygon. Okay, so this is the regularity lemma that we have. Until now, I've only talked about existential results. We want to use it algorithmically, so we would also want to get such a partition. First of all, the next question, yeah, you basically follow this usual strategy of proving regularity lemmas, which is to iteratively refine partitions until you get the desired property. And it can be shown that this process only lasts based on some energy argument. And this is like a standard Friesen and weak regularity argument. Algorithmically, there's an extra question. How do we find this? It turns out that it's really, to implement this process algorithmically, we can rely on a standard problem called cut norm, and we only need to solve it approximately, not exactly. And that approximation algorithm from Allen and Naur is well known, and we just use that. In a different codes context, we showed that this cut norm approximation algorithm can be run in near linear time. So it's based on solving and then rounding an STP, and that STP can be solved in near linear time. And this is the only nonlinear time step of the algorithm. Everything else is just linear. Okay, so we started with codes, then we went to all these graphs and sets, etc. Let's map these two. So recall that our setting was this, that we decoded each of these local views and ended up with lists of size 1 or 2. First of all, let's assume that every list on the left is of size exactly 2. If it's 1, we'll just pad with extra elements. And let's also say that we arbitrarily order these elements. So now we have this sort of picture where each local list is of size exactly 2, and these are ordered, first and second element. Based on this ordering, we define 2 graphs. Okay, first, let's fix a global code word edge. The graphs don't really depend on this global code word edge. Now we define, sorry, before going to the graph, we define 2 subsets which basically correspond to where does this code word edge lie in each of the left vertex? Is it the first position, second position? That's all these subsets are encoding. So A1 says that in each vertex in A1, the code word HL is the first one. In A2, it's always the second. And these are going to be disjoint. And it's not difficult to show that finding H is equivalent to just finding A1 and A2 up to some small error. So at least finding the code word H can be reduced to finding some sets A1. Now, let's construct 2 graphs, H1, H2, that we can construct algorithmically. So you should check that none of these definitions should depend on H, because H is the unknown quantity. We construct 2 subgraphs, H1 and H2 of the expander G by deleting some edges. How do we delete the edges? For H1, we just look at each left vertex here and the left assignment. Wherever it disagrees with the local GL, we delete that edge. And for H2, we do the same for the second assignment. So for each left vertex, we look at the first assignment. Where does it disagree with G1? We delete that edge. So for H1, we delete all edges of G for which FL1 and GL disagree. Same with H2. And this can be done algorithmically, right? Because we see GL, FL1, FL2, all of these are clear to the algorithm.
And you can take a worst case ordering of.
Yeah, so this is arbitrarily ordered. Okay. Now for these H1, H2, we will apply the sparse regularity lemma. These are going to be dense subgraphs of the expander G. And we will want a partition that works well for both. So let's just take their common partition, the common refinement. That just ensures that this partition works for both of these together. The main claim is that the set A1, A2, which corresponded to the hidden code words location, would have density very close to 0 or 1 on all of these parts that we have constructed algorithmically. Okay. If we can prove this successfully, then the algorithm would simply be to look at each part in P, which are only constantly many, and try out.
Sorry, what is A1 and A2?
A1, A2 is just encoding the location of the hidden code word H, whether it's the first code word or the second code word. So we said that finding H reduces to finding A1 and A2. So P is in our hands as the algorithm, and we are saying that A1, A2 will have densities very close to 0 or 1 on these parts in the partition. Once we have this claim proven, the algorithm would simply be to enumerate for each part whether we entirely take it or don't take it.
Are you using the fact that one is the complement of the other?
It's not necessary, I think, but
like if you have 3 elements in the list, like, couldn't one set just kind of be noise or something? Like one doesn't have to correspond to a global code or
no, like A1, A2 are always corresponding to where the true code word is. So these will always be disjoint.
But they may not cover the whole.
They may not cover the whole list.
Okay.
Yes.
Yeah, okay,
Yes.
so that's
in fact, they will also cover the whole list because of the sampling property. So the true code word H must be present in most of the local lists.
At most, not all.
Almost, yeah. But that error is of the order of lambda, so we can make it as small as we can. Okay. So yeah, like once we have this claim proven, the algorithm is simple. Just look at this regularity partition, do brute force enumeration.
I guess you're sort of using the fact that you don't delete too many edges from G to create H1 and H2, which is
Yeah.
that you can apply the regularity.
Yeah, but that's okay because these Fs were literally defined to be close to GL.
Yeah.
So they are not going to be insanely far from GL. Okay. And this claim is what we call some combinatorial rigidity. The fact that these sets go concentrate as 0, 1 density is a rigidity phenomena.
H1, capital H2 do not depend on the errors or anything. I mean, this is easily computable.
Yes.
Capital A1, capital A2 are not a
They are the hidden objects that we are looking for. Okay.
And is it clear how you find A1 and A2 given this main claim?
Yes, because
Okay.
you just look at this refinement P.
Okay.
This is going to be constantly many parts. You try out whether you will entirely take the part or entirely refuse it.
You go over all possibilities.
Go over all possibilities, and then you'll be very close to A1 or A2. And the error that you accrue in the process can be taken care of by the unique decoder of the base.
So just to check, if you have this like eta parameter floating around and the number of parts is like exponential in that, and so then the running time of the algorithm will be doubly exponential.
Yes, but we have some fixes for that would make it singly exponential.
Okay.
In fact, you have some fixes that will make it a tower.
Okay. So to argue this, let's say B is the set of right vertices where G and H agree. So what do we know? B is fractionally going to be R plus epsilon. There should be fraction. It's going to be R plus epsilon if we have list decoding in the regime of 1 minus R minus epsilon. What we know for sure is that if we look at this edges between A1 to B, then none of those would be deleted when constructing H1, because H1 was literally corresponding to deleting edges where the first assignment is differing from GL. The first assignment in A1 is equal to the true thing, true assignment H. So none of the edges between A1 and B will be deleted when constructing H1. So we went from G to H1, which is like a dense subgraph. We deleted a bunch of edges, but we completely left this portion intact. And that is roughly what allows us to recover this set. Right? So there is this product A1 cross B that we did not touch at all. So suppose A1 was not almost 0, 1 on the partition B, then there would exist some A1 star, which is, like say, there was some part where A1's density was 0.5. Then I can pick an A1 star that looks somewhat different from A1 while still having the same density under that partition. So if one of the parts, the density was 0.5, then I can pick a different A1 star which still has the same density. Okay. And this A1 star would also satisfy the fact that no edges were deleted, because as far as edge counts are concerned, A1 and A1 star are giving the exact same. We argue that a very different A1 star from A1 cannot have this sort of property.
So it won't be.
Yeah.
So I mean, there is a list of possible code words which could be agreeing. Each one corresponds to a different A1, A2.
Right.
And then you're saying, well, so why can A1 star not be from the other list? Or maybe, okay, no.
Yeah, so we already fixed an edge in the beginning. A1 is corresponding to that fixed edge. So all of this is to say that for a fixed enumeration choice that we are making, there would be a unique code. So there is an implicit list size bound also. Yeah.
Sorry, so the second bullet point says like, so, okay, so suppose that A1 is not almost 0, 1. So let's say that it has like 0.5
Yeah.
Somewhere. Sorry, is it obvious that it exists an A1 star that's?
Right, so you pick an A1 star that is disjoint from A1 on that part.
Okay.
Density wise, it would still look 0.5,
I see.
but it is quite different.
Okay. Right, because that part is very large. It's like
That part is very large. It's like a constant. Exactly. Yeah.
So Shashank, there will be some errors here, right?
Yeah, everything has errors.
All
Here,
equalities.
yeah, all these equalities. No, the second equality is true equality. The first one has errors. Yes. Okay.
I mean, if A1 star is disjoint from A1, how can can it be the same set?
So that's the size.
It's the size, it's just the size.
Oh, yes, that should be size. Yes. Yeah, maybe I define EH to be just okay, so we have this setting where B is like the right agreement set, and we have two sets A1 star and A1, both of which have almost untouched edges when constructing H1. So why can this not happen? So recall that B is at least R plus epsilon, which means that most left vertices will have roughly R plus epsilon fraction of edges going into B. That's again sampler property. It's an expander, so you expect the right number of edges in each neighborhood to go into that B. But for any vertex in A1 star that is not in A1, the local list code word is different from HL. That's the whole point why it is not in A1. So you are changing some 1 minus R fraction. That 1 minus R will start intersecting with R plus epsilon. And what will happen is that some of the edges going from A1 star to A1 star to B would end up deleted. But we said that we are only considering A1 stars that are that have almost untouched, no edges were deleted from A1 star to B. So that cannot happen.
So there is like only an epsilon fraction of edges that are coming from the second bullet, and so this third bullet has to be accurate up to that
Yes,
epsilon.
yes.
Okay.
So lambda will have to be adjusted to account for this epsilon all the time.
Yeah.
But it all works out. Okay. So let's move on from the proof a bit. The final algorithm would look something like this. Let's say we have some received word G. We use it to compute these local lists. There are two of them for each left vertex. We use these local lists to construct graphs H1 and H2. All of this can be done algorithmically. Now, based on these graphs H1, H2, we find these partitions P1, P2 based on the regularity lemma. Take their common refinement. That's easy. And then just brute force enumeration over all sets in P. That's going to be constantly many parts. We try out all possible assignments of 0, 1 onto them. And we'll find something that is very close to A1, A2 partition. The final base code's unique decoder will just correct the errors that we collect in the process.
So the only list decoding step is this brute force enumeration.
Yes, yes. And that is what corresponds to the list size. The list size is just going to be 2 to the size of this partition.
And all the arrows except for the down arrow is linear time.
Yeah, so only the part where you find this partition, yes, exactly, the down arrow. Everything else is linear time.
And
If I ignore algorithms, also the combinatorial implication of this, if I have any outer code with any kind of decent distance at all,
right,
the AEL version is
yes,
decodable up to capacity.
Yes. Yes. So you start with any code that is barely unique decodable, do this process, and you'll get something that is list decodable up to capacity.
And the new inner codes need to be list decodable up to.
Yes,
Oh,
so
right.
but that's sort of part of the amplification process because it's constant sized.
So you said you needed some properties of the inner code, but there seems to be nothing.
So the only property that I need is that when I do this decoding, there should be only constantly many things. Here I have assumed 2. We can deal with any constant. It should not depend on D. Right.
Yeah.
Because once it depends on D, it starts racing with lambda itself.
So that's just like good list decoding properties of the inner code.
With constant list size.
Up to capacity, you need up to capacity.
Whatever radius you have for the inner code will get corresponding thing for the global code.
If you just know Johnson bound or something,
you can get something for the Johnson. Okay. We had these 3 codes. Actually, both of these techniques are applicable to all these 3 codes. So you can have 6 different algorithms.
The sum of squares is slower.
Yeah, so now I'm going to talk about some of the sum of squares issues. Sum of squares tend to be far slower. And typically even the exponent of n is unbounded. There's no fixed number like 5 or 6. And SOS is mostly an algorithmic technique, but regularity lemmas can lead to both combinatorial and algorithmic results. SOS, there is, like if you're using SOS, that's only for the algorithms. But regularity lemma seems to give results even for combinatorial.
So does that mean that SOS algorithms work only that they use the combinatorial list decoding bound to get an algorithm version?
Exactly.
I see.
Yeah. Yeah. So SOS follows the proofs to algorithms paradigm more closely. Like it looks at a combinatorial proof and that immediately suggests some natural algorithms, and you just try to implement that algorithm. Regularity lemma based algorithms can require a bit more creativity. But in the process, they might give new combinatorial proofs.
Are there instances where the SOS toolbox gives better results than the regularity toolbox?
Yes. Okay, so let's look at the implications for these different codes. For Tanner codes, okay, yeah, so we mostly talk about AEL codes. For Tanner codes, if the local code has distance delta 0, these codes have distance approaching delta zero square up to lambda. And these regularity based methods can be adjusted if the local code was also list decodable up to delta zero. Then we'll get list decodability up to delta zero square. If it was a smaller radius, like you asked for Johnson bound, in the Tanner code case, then it would be delta zero times the local code's decoding radius. And that is exactly the case for their dense analogs, which are tensor codes. For tensor codes, if you have list decodability radius for one of the constituent codes, you get the distance times that list decoding radius.
So in Tanner codes, you don't lose in the alphabet size. It's the same. You start with some small code and you have a code of the same alphabet.
Yes. Yeah, so all of this would even be applicable for binary codes. And here, regularity lemma is the only known way to control list size beyond Johnson. Without that, we don't even know how to combinatorially say anything beyond Johnson bound. For AEL codes, what we talked about was list decoding. You can also use list recovery because all we cared about was a list size bound for the local code. And we can do all of this in near linear time. For AEL codes, actually, there are two ways of controlling list size. One is regularity lemma that we talked about. The other one is more generalized singleton bound style arguments that directly give a sharp 1 over epsilon list size. And that's something that we'll talk about and we'll hear about in the next talk. And roughly speaking, regularity lemma for AEL codes can be seen as analog of the Guruswamy-Wang result, which says that the list is contained in a small dimensional affine subspace, and then you do enumeration to find that list. Here, the analog of the affine subspace is this low complexity partition. And after that, you do brute force enumeration. So in this spirit, the next result that Madhur will talk about will roughly be the analog of Chen and Zhang result for expander. And then the third one is announced binary codes near GB bound. These can also be list decoded up to a radius approaching half. And then not just binary, there are also extensions to larger alphabet. Here there is an advantage that SOS decoders enjoy, which is that SOS can decode up to the Johnson bound. The radius achieved by the regularity lemma is not as good as the Johnson. It approaches half, but it's at a much slower rate. And this is the only place where I think SOS now enjoys superiority over regularity lemmas. And for these codes, it's open to do anything beyond the Johnson bound, which would be very interesting. Because for binary codes, we don't know good capacity achieving both sides. The final thing that I wanted to talk about was just using codes as an algorithm design tool. So what we roughly saw was that sparse regularity lemmas can be used to stitch together local candidates into a consistent global one. This problem arises not just in codes. This consistent stitching problem also arises in applications like heavy hitters, compressed sensing, group testing, etc., where the typical choice might be to use a list recoverable code. Even in AEL, once we have these local lists on the left, the older choice was to use an outer list recoverable code. But what we are showing is that you don't need an outer list recoverable code. You can do a unique decodable code and still use more of the structure of these local lists. Can we do something similar in these applications? Do we have to rely on black box list recoverable codes? So there are different applications where black box list recovery is used for these applications. Maybe we should be replacing those, at least some of those, by expanders along with regularity lemmas. And it's not a coincidence for heavy hitters. There are already some approaches that are based on graph decomposition, clustering, etc., which are close to these regularity lemmas. These are two ways of doing this. Maybe it's not a coincidence.
Thank you. And maybe we can have some questions by the next speaker. Yes.
So your consistent stitching thing seems very general, right? Can we be viewed as some sort of unique games algorithm on expanders? Because you're saying that number of
Yeah.
dimensions is bounded and you're finding them all.
Right. Yeah, I mean, we haven't tried unique games, but it's completely believable that it should.
Because I mean, really, this finding the consistent thing is
Right,
finding a copy of this expander in a lift.
right, right,
It's like solving unique games.
right. Yeah, I think that should be doable, but not sure exactly how difficult it might.
I guess all the results you shared were for explicit codes. Is it feasible to say have like some distribution over codes? You sample a code then with high probability, like you could get an efficient decoding algorithm?
One way could just be, for example, if you are witnessing the random property you're witnessing is, let's say, spectral explosion.
Yeah.
Kind of thing.
Yeah, then that's fine.
Then that's fine.
But what if
But if it's like unique neighbor expansion, etc., then I don't know how to witness that, or like,
so in general you need, if you have a property you can witness, it's fine, but beyond that.
possibly, yeah, if it's a property that we don't know how to witness it.
Questions? Okay, right there. Okay, so. Okay, so we'll continue with the same line of work. Our next, you want to wait for 5 minutes or?
No.
Start early, we're early for lunch. Great. Okay,